Welcome to our first lecture. This will be on section 1.1. This will be the manner that we will typically do this. I will post these study notes online and you will be able to read them at your own leisure. So during the lectures, I may not necessarily read every word that's on here. But let's get started. This first lecture is mostly going to be about explaining the most basic definitions and what we're going to be doing with this course. So this course is on differential equations. A differential equation is any equation that contains a derivative. So it doesn't really matter what else is going on in here. As long as there's a derivative, we can safely call it a differential equation. Now, it could be a first order derivative. It could be a second order derivative. There could be multiple derivatives. It could look like this. We've got multiple derivatives in here. Some of them are higher order. It all makes a differential equation. Now, the first distinction we have to draw is between ODEs, or ordinary differential equations, and PDEs, partial differential equations. An ODE is probably exactly what you're picturing. It's some equation that has what you're familiar with thinking as a derivative in it. But there are a couple different ways that we, from Calculus 1, learn to write derivatives. You can write it as y prime. Sometimes we write it as dy dx. But these are both the same equation, we know that. So these are both different types of ordinary differential equations. Where the distinction comes in is where we get these partial differential equations. So what may or may not be a rehash of something you've already learned, depending on what courses you've taken. I will explain now what a partial derivative is. So we're very familiar with ordinary derivatives. We have some function of a single variable. Maybe it's 3x squared plus 2. And then we take the derivative of that. And in this case, we know it's equal to 6x. But sometimes we have equations of multiple variables. What if f was a function not just of x, but also of y? And let's suppose it is 3x cubed plus 4y squared. Well, I can't just say what is f prime of xy. It doesn't really have a definition, honestly, because we don't know what we're taking that derivative with respect to. So we could take it with respect to x, in which case we would get the answer 9x squared. Or we could take it with respect to y, in which case we would get the answer 8y. But it's not clear just based on that notation, so that's why we would never use such a notation. Think about the Leibniz notation, the dx dy. For a single variable, we use this dy dx sort of notation. Here, we're going to do something similar. If we took and we're going to use this delta instead of d to recognize that this is a multivariable function. If we take delta of f with respect to x, that's the one that's going to be equal to 9x squared. If we take delta of f with respect to y instead, that's the one that is equal to 8y. We have taken the derivative of the multivariable function with respect to x or with respect to y. So a partial differential equation is any differential equation that instead of having ordinary derivatives in it, has partial derivatives. So an example would be df dx plus x plus 1 equals 0. That's a partial differential equation. Okay. So now we'll move on to a few examples. Hopefully clear this up a little bit for us. Our first example, f of x is equal to x squared plus y cubed plus 1. And we are asked, is this an ODE, an ordinary differential equation, a PDE, a partial differential equation, or neither? This one clearly is neither. There's no derivative in there. we have many different ways that we write derivatives, the Leibniz notation, the partial Leibniz notation, or just the prime notation. None of those are here. This is just not a differential equation at all. So this is neither. Here, if you were looking to point out a derivative, you would find this one written in Leibniz notation, dx dy, and no other derivatives, certainly no partial derivatives in there. So we would say that this is an ODE. Our next one, we have a couple different derivatives. We have the derivative of z with respect to x and the derivative of y with respect to x, but we don't see any of this partial Leibniz notation, so this is ordinary. Next, we see an equation that has lots of variables in it, but there's no derivatives. There's no primes, there's no Leibniz notation, so this is again neither. Next, we're finally seeing some Leibniz notation here that is in the partial form. We see these deltas instead of d's. So remember, what that means is that this z function must actually have a couple different variables in it. And you can see there's a delta z delta x and a delta z delta y. So z may look something like z of xy is equal to, and then whatever, maybe it's 2xy plus x plus 1, whatever. So this is partial, that's the point. Since z is a multivariable function and we're using these partial derivatives, this is a partial differential equation. Next, we see something written in prime notation. And since it's clearly not written in partial notation, this is ordinary. And then finally, we have some more Leibniz notation. We see these deltas. Deltas come from the partial definition, remember? So that means that z is, again, some multivariable function. Here we're taking the second derivative of z with respect to x. And while there's no y mentioned, there is some other variable, a, b, y, whatever you would call it, at least one other variable in this z function, because we're only taking the partial derivative. So this is a PDE. Simply put, to find a PDE, you're looking for that delta notation. For an ODE, you're looking for any other derivative. And if it doesn't have either, then it's neither. Okay, moving on. It will often be very important in this course to understand which variable is dependent and which is independent. So we will mostly use Leibniz notation. Note how the y prime notation is very quick and easy to write, but it doesn't tell you what the independent variable is. It doesn't tell you what you're taking the derivative of y with respect to. So while we will sometimes use this, in this course, we're mostly going to be using the Leibniz notation because there's just more information in the Leibniz notation. Think back to y prime versus dy dx. Y prime may be a little quicker to write, but it doesn't tell you what the independent variable is, what you're taking the derivative of y with respect to. So usually we're going to stick with Leibniz notation, but we may sprinkle in some y prime just so that we're comfortable with both. Also, it's important to note that partial derivatives, while I've explained them as being written as delta of something with respect to delta of something else, it can be written in a shorthand as just z sub x, or some variable sub another. So now we'll do a quick explanation of a Leibniz notation in case some aren't as comfortable as others with it. So dy dx means the derivative of y with respect to x. But how do we represent the higher order derivatives? We're going to act like d dx is kind of this action that you can apply to both sides of an equation, taking the derivative. So if we suppose that we have the function, let's undo that. If we suppose we have the function y is equal to x squared plus 2, we would take d dx of both sides, and that's taking the derivative of both sides, essentially. And that would give us that dy dx is equal to, well, the derivative of x squared plus 2 with respect to x. Notice how this notation tells you what it's with respect to. So with respect to x, it is 2x. So that's how we reach our answer. But now we ask, how do we do higher order derivatives? And you'll see, using this algebra we have here, if instead of taking the derivative of y with respect to x, we are taking the derivative of dy dx with respect to x, in essence, figuring out what that y double prime is. What is the second order derivative? Using this algebra, it shows you why the Leibniz notation ends up having this 2 in between the d and y in the numerator, but after the x in the denominator. So in case you ever wondered why Leibniz notation is written in that manner, this algebra should clear that up, where we're taking the derivative with respect to x of an entire derivative, and it simplifies like so. Next, we'll look into the order of a differential equation. So that is the order of the highest derivative in the equation. So we've got an example here that may be quite helpful. Blow it up a bit. So d squared y dx squared, we would never read it that way. This is just the second derivative of y with respect to x plus 5 times the first derivative, or dy dx cubed, minus 4y is equal to e to the x. And the question is, what is the order of this? And I've chosen this example because I want you not to get confused with what these different exponents mean. So we're going to clear that up now. We've just learned that when we see this 2 or any number in between the dy and after the x, that is actually talking about how many times you're taking the derivative of y with respect to x. So we've taken the derivative of y with respect to x twice in this equation, whereas this here is the first derivative cubed. We've only taken the derivative once here, but then we decided to multiply it by itself 3 times. So that cube represents an exponent in the traditional sense and not something that would be measuring the order of the differential equation, because the order of the differential equation asks what derivative is of highest order, or which derivative represents the most times you've taken the derivative of y with respect to x. So this is a second order ordinary differential equation because it's the order of the derivatives that matter, not the largest exponent. Okay. Move on now to linearity, and this will be our last new concept for this video. An nth order ordinary differential equation f is linear if f is linear in all of these variables: y, the first derivative of y, the second derivative of y, all the way up to the nth derivative of y. So, written out more explicitly, that means that f is actually just a sum of all of our derivatives of y being multiplied by some function of x. So you can see how there's many ways that things would end up not being linear. If I have some derivative of y, suppose it's the second derivative of y, d squared y dx squared, but instead of multiplying it by a function of x, if it was multiplied by y, plus dot 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 plus dot dot dot, whatever else is in there, this thing is not linear, because my definition of linearity says that every derivative of y plus y itself all have to just be multiplied by functions of x. So we'll look into these examples to hopefully clear up any issues. The following are linear first, second, and third order ordinary differential equations, respectively. This first example is a good one to look at because immediately we don't even see a derivative in there. We see these dy and dx variables, but they don't really mean much unless they're put together. So we're going to have to do a little bit of algebra here. Now that I've moved my y minus x over to the right side here with the dx along with it, I can divide both sides of this by dx. And now I'll just move that 9 minus x back over. So what we've done here now is we have dy dx, and it is multiplied by some function of x. That's good. And we have some function of x here not being multiplied by any y at all, but that's fine because that's what this g of x represents in our definition of linearity. There can always be some function of x left over that is added on. So this is clearly linear. And it's first order because we've only taken the derivative of y once. In the second example, we see that this is quite clearly linear. The things being multiplied by y are just 3 and -1. Note that we say they have to be functions of x, but 3 is a function of x. You can say that 3 is equal to 3 times x to the 0. So that is trivially true that 3 is a function of x. And then clearly it's the same with -1 and of 8. So in case you had any doubt in your mind whether these constants count as functions of x, they do, because they're kind of arbitrarily so, because they could be multiplied by x to the 0. And what order is it? Well, it's a second order because we see there is a double prime here. So one of the variables is a second order derivative. Finally, our third one here, well, we're seeing that it's third order because we see we're taking a third derivative using our Leibniz notation. But now we need to figure out if it's linear. Well, the third derivative of y with respect to x is being multiplied by x to the 6, which is clearly a function of x. dy dx, the first derivative, is multiplied by 3x, again, clearly a function of x. Y is multiplied by -1, and then we have a +1 here. The only work that may need to be done is we may need to subtract 4e to the x from both sides so that it comes over. But it is also a function of x, so everything's good. This is linear. So we'll conclude now with looking at some examples of nonlinearity. So you can pause the video for a moment if you'd like to think, but figure out why is this first equation not linear? And the solution is we have a y double prime, a second order derivative, but it's not multiplied by a function of x. It's actually multiplied by y. That immediately tells you that this is not linear. Again, pause the video if you like to take a moment to think about this second one. Why is this not linear? Well, we can move everything over to the left, leaving 0 on the right to try to make it look linear. The problem is this tan y, because y is simply meant to be multiplied. If we look back up at our definition, the only y term is one that is multiplied by some function of x. So you can't actually have y itself contained within some smaller function, some tan y or sine y or ln y or e to the y. None of that is going to fly if you're looking for linearity. So because of the existence of this tan y, this is not linear. And now finally, you can take a moment to think about this one. Why is our final example here not linear? Pause the video if you'd like to have a moment to think. The problem here, it's clearly not the 1 that is multiplied by y cubed, or sorry, that's not y cubed, that is y triple prime. It's not the 3 that is multiplied by y, and it's not the 0 over here. That all falls into our definition. It's the y squared term. If we look at, again, what y looks like in our definition of linearity, y needs to be multiplied by some function of x. But here, y is actually multiplied by y to give you y squared. And y is not a function of x.